scheduled on Thursday for center review. So what we're going to do is we're going to put the last bit of CNN. I didn't forget about that. We still need to talk about the kernels and so on. But you didn't need to have that for your first milestone. So Carl is going to come here on Thursday to finish up the CNN part, so that you'll be able to have the complete knowledge about the kernels and so on for the CNN as you move forward. So I'm going to move ahead and talk about reduction trees so that you can do the lab, which is MP 5.1. Okay, so we do a little bit of readjustment, but we should be able to make everything to work. This is part of the readjustment of the timing, so things get a little bit, I would say a little bit shaky, but I think at this point we should be able to get all the schedules to work from now until the end of the semester. You probably have seen that we readjusted all the lab due dates, so it should match up with the lecture. Okay, so this used to be the lecture that is right after convolution. And for matrix multiplication and convolution, we essentially take a bunch of input data in the two-dimensional matrices and so on, and we generate an output that is also two-dimensional matrices. And each output is independent of others. So the threads don't really write into an area where other threads are concerned about. And so those are very easy independent execution patterns. We truly have the situation where we can divide up the data, output data, and have every thread to be responsible for one or part of the output. And they can operate totally independent of each other. And this topic is now transitioning into the realm where the threads need to begin to collaborate more. Okay, they need to begin to to have potentially generating output for each other, and so we're going to look into this as a kind of the next level of patterns that we're going to to use in our code. So the reduction tree is arguably the most widely used parallel computation pattern, and we're going to talk about the basic concept and the class of computation. Reduction tree really represents a class of computation. It's not just a single algorithm. And we're going to be looking at things like memory coalescing and control divergence, as we craft the code. And then we're also going to look at a very important concept, which is thread utilization. And this is the sort of the beginning where we're going to see that some of the threads will be underutilized. Okay, so we have some design options to be able to improve the thread utilization by playing with some of the thread indices and so on as we move forward. So the concept of reduction trees actually roots from the partition, the concept of partition and summarize. In some cases, we say divide and conquer. Okay, and so it's a very commonly used strategy for processing large data sets. Remember, when we process large data set, the end objective is to be able to make some kind of decision, right? So we naturally want to be able to take a very big data set and at some point want to be able to hammer it down into smaller and smaller amount of data, but better and better quality information, so that in the end we can make some decision, we can make some conclusion. And we saw that in the in the classifier, in the machine learning, sort of the feed-forward networks, where we have a fairly big input data, which could be a let's say a picture of pixels, and at the end we want to be able to have a classifier and then tell us which category, right, this particular picture belongs to. So we go from a big amount of data to a small amount of data, but hopefully a good, meaningful information in the end. So so we oftentimes need to be able to partition the big data and then somehow summarize it into the into a smaller and smaller amount of data. And reduction trees are the primary vehicle for us to, to kind of hammer down the amount of information. So in order to have a parallel reduction tree, we need to make sure that there's no required order of processing in a data set. So this means associativity and commutativity. So for example, when we do addition, integer addition is truly associative and cumulative. Commutative means that doesn't matter if you add A to B or B to A, right? It doesn't matter. So, and also it does, that's commutativity. And also when you add three numbers together, it doesn't matter whether you add the first two together first or you add the second and third one together before you add that other number. So that's associativity. So whenever you have both associativity and commutativity, you are able to perform your summary in any order you like, and so on, that you have the complete freedom to perform things in parallel. And in parallel, when things can happen in any order, and then you can change the order to get more parallelism. So oftentimes, we would partition the data set into smaller chunks, okay? And this is very, very important, to be able to, to do so. And then we have each thread to process a chunk, and then we use the reduction tree to summarize the results from each chunk into the final answer. And so we'll focus on the reduction tree step, and at some point you will begin to see that the partitioning and so on can also make a difference. But we'll focus on the last one, which is how we take the partial results and then we use the reduction tree to generate the final result quickly. And for those of you who are familiar with distributed computing, the Google and Hadoop MapReduce frameworks are examples of the reduction trees. The reduce part of these MapReduce frameworks use the reduction tree very extensively in those frameworks. So the reductions can also be used to enable other parallel computing techniques. So for example, reduction is often used to clean up after some commonly used parallelization techniques. So one of the important parallelization techniques that we'll be learning later on during the semester is privatization. Oftentimes, we have a situation where multiple threads need to write into the same output location, and they will have some contention. Okay, we're going to learn about atomic operations that will be used to coordinate these potentially conflicting writes into the same location, but they also serialize the activities. So we want to be able to minimize serialization in our parallel computing, and therefore what we do is we try to avoid atomic operation, avoid serialization by assigning a private location to the individual threads, so that they will just keep updating their private locations, and then at the end we use a reduction tree to summarize these private versions into the final version. Okay, we combine all these private versions into the final version, and we're going to actually see a lot more of that in the histogram computation pattern. So the main thing is the reduction trees can be used to combine these private version values into the final version. So that's why it's very, very important that we know how to use the reduction tree, implement the reduction tree in as efficient as possible. These things are heavily used in real parallel computing problems. Okay. So let's go into the nitty-gritties. What is a reduction computation? The reduction computation is defined as using summarize a set of input values. So you have some kind of input value set, and you want to summarize that into one output. Okay, and the reduction operator or reduction operation could be max. Max means that you want to find the maximal value in that input set, right? This is a useful piece of information. And you can find the minimal value of the input set. You can add them up. You can find the sum of among all the input values, and you can use product. You can multiply all of them together into a product. The bottom line is you're trying to produce one value out of a set of values, right? And the reduction operator in each one is max is going to be greater than, right? And then min is going to be smaller than. And sum is going to be just addition. Multiply is going to be, product is going to be multiplication. All these operators need to be associative and commutative. So this brings us to a kind of a subtle issue. Integer integer addition and multiplication are truly commutative. If you take an integer addition and you try, you look at the addition, whether a plus b is equal to b plus a, or when you have three values you want to add together, it doesn't matter which pair you add first. But when it comes to floating point, it actually is, strictly speaking, floating point numbers are not strictly associative. The reason is floating point representation is approximate. And you're going to have a situation where if you have a very big number and very small number to add, the floating point arithmetic will line up the exponent part, will make the exponent value the same. So if one of the values is very, very small, the process will actually make what we call the mantissa part extremely small. And in some cases, when you add the two together, the small value may disappear, okay? And so this is the fundamental reason why if you add, let's say, a big number to two small numbers, you oftentimes will have different results. If you add the two small numbers together first, then together they form a little bit bigger number, and then you add it to the big number, then you will have some effect. But if you add the big number with one of the small numbers, the small number may disappear, and then you add another small number, the small number will disappear too. So that will give you a situation where the order of adding these three numbers will be different depending on which pair is added first. The football players know this very well. And I don't know how many of you watched the Super Bowl at the very end. And these people know exactly how the floating point numbers work. Okay, don't underestimate the intellectual strength of some of these football teams. So what happens is that the Eagles actually have extremely big the running backs. So you probably saw that at the early part of the game, you have a couple of these people. The running back of Eagle was charging into the end zone. And then you have, one of the Patriot players trying to grab the person and get dragged along for a little bit, and then they just kind of got, fell apart. And then another person tried to grab that running back and fail, right? So they keep scoring. So towards the end, the Patriots figured out that they actually have, more than one, oftentimes three people. You should go back and see, how they play. They have three people, sometimes four people, all jump on that running back at the same time. Right? And that's how they can pin the running back down. And so think about this as the lack of associativity. You have to make sure that all these guards bind together and pin down that huge running back that is running towards the end zone. So this is the mental picture that you should be thinking about. And Chicago used to be to have someone called William Perry. And the refrigerator, you should go back, go on the website and see Mr. William Perry. And he used to be able to run through the end zone with four people on him. Okay, so that's the kind of picture that you should be looking at. If you add a large number of these small values together before you add it to a big number, then you have a chance of making a difference. This is the fundamental reason why when you do parallel computing, different algorithms, different reduction algorithms may give you slightly different value because some of the small values can disappear in that process, but if you use a different ordering, then the small numbers may not disappear. And this is expected. With floating point arithmetic, oftentimes we need to allow a little bit of variation of the end result value because of this phenomenon. Okay, and this is something that any parallel computing programs need to be able to account for, in their, in their computation. So it has to have, the operators that we use in the reduction also has to have a well-defined identity value. That is, there should be a value when operated with another value, that other value will always come out. Okay, so for example, for max, the smallest possible value should be the identity value for the operator, because it will be always, whenever you ask if a value is greater than this value, the answer is yes. That value is always going to be greater than the smallest possible value. In our floating point numbers, it will be the negative infinity for practical reasons. And for some, the identity value will be 0, because 0 added to any value will be that other value. So the 0 is the identity value, and product is 1, right? And when you multiply 1 to any value, the outcome will be that other value. So each of these operations has a well-defined identity value, and so this gives us the the ability to perform parallel computing on any of these operators. So this is reduction is an important category of what we call the collective operations. For those of you who will be taking, let's say, Mark Sneer's, MPI class, or the, Sanjay Kale's MPI class, you will be learning the MPI collectives, and the MPI collectives are the equivalent of these reductions. In fact, one of the important category of MPI collectives will be the reduction reduction API calls in MPI library. So let's first look at an efficient sequential reduction algorithm. If we need to take an array of numbers and we add them together, there's a very efficient way to do this sequentially. We just go from element 0 all the way to the max number, the max index. And for each position, we just do a reduction operator with what we currently have. So, for example, if we're trying to find the max reduction for a whole set of numbers, then we initialize the result as the identity value of max, which is the smallest possible value in your system, right? So we initialize that. And then we go through every data value, and we ask if this data value is greater than the value that we currently have in hand, which is we start with the minimal possible value, the smallest possible value. So the first element is going to replace that, right? The first element would definitely be bigger than what you got. And then you will go through every position and ask the same question. If the current position value is bigger than what you have in hand, then you do the swap, right? So at the end, you will have that max value. So this is a very efficient sequential algorithm. It only visits every value once, and so it's an order n algorithm, and it's very, very efficient because you have a pointer that you just keep increasing to the next element. So there's very, very little fat or extra overhead that you have in that sequential algorithm. This is very important to remember, okay? These are the lean and mean sequential algorithms that oftentimes trip the parallel algorithms. The parallel algorithms will likely cause more overhead. So if you're not careful, you can actually be slower. The parallel algorithm can have enough overhead to run slower than the sequential algorithm. Okay, so this is very, very important to remember. So we iterate through the input and perform the reduction operation between the result value and the current input value and what you had as the temporary result. And you go through all the positions. In the end, you get your reduction. For sum, it's the same thing. You start with 0 because 0 is the identity value of sum. And then at every position, you just add the current value into that sum value. So in the end, you will get the total of your set. So here is a conceptual picture of how we can do this in parallel. This is a reduction tree, and this tree is conceptual. We don't have any pointers, we don't have anything that represents that tree in our memory, okay? This tree is really just the conceptual data flow in your computation and towards the final result. So the tree is really an imaginary tree, okay? It's not a data structure tree per se. So what we have here is we have the initial list, so 3, 1, 7, 0, and so on. And we want to find the max value. We want to find the max value in this list. So what we do is we have 4 parallel threads. Each one will find the max value of a pair, okay, of a pair of these input values. So after the first step, the 4 threads will each have a champion, right? A local champion. And that local champion is the bigger value between the pair, of the pair. So now, for the next round, we only have 4 values that we need to find the max value for, because only the bigger ones are the contenders of the final one, right? So now we only need to have 2 threads, and each thread will be comparing the 2 values generated from the previous round. And so at the end of the second step, we will have the champions among the initial 4 elements, right? The initial 4 elements. And in the end, we have these 2 compared by 1 thread, and then we generate the final result. So it should be clear that we only need to have log n steps in order to be able to process n elements, because each step whittled down the data size by half, right? So you have, you start with the full numbers, and then each one you divide the number of elements by 2. It only takes log n steps for you to get 1 element out of this process. So this is the fundamental reason why reduction trees will give you speed up, because instead of taking a linear sequential process and take n steps to get your final answer, using half n number of threads, you will be able to get the answer in log n steps. Is this good? If it's 8 elements, we will be able to do it in 3 steps. So it's a pretty good speed up. But if you have 1,000,000 elements, and log n is going to be 10, right? So 1,000,000 steps, 20, 2 to the 20. So you have 1,000,000 steps versus 20 steps. So that's when the speed up is going to be really, really big, right? On the other hand, there will be inefficiencies in the process, so we're going to go through that, okay? Now, the world has been using reduction tree, for a long, long time. And any tournament that we see are reduction trees. Okay, so this particular picture is the 2010, I believe, 2010 World Cup soccer tournament in South Africa. Okay, so coming into the tournament, there are 8 teams that are the regional champions, right? So they come into South Africa. And then, so we actually have, 8 teams that were going to get a max reduction. So the champion of the team is finally the max among all the initial 8 teams. So we have each game is an operator that produces a winner, right? So it's a greater than operator. And then we have, after the first round, we have 1 game, 2 game, 3 game, 4 game. So those are the initial 4 threads that we saw in the previous picture. And that will give us 4, winners. And then we use, the second round, which is the pairwise game, the semifinal games that produce 2 winners. And then the final game that produce the world champion, right? So this is a better rendition of the reduction tree from the artistic point of view. This actually looks a lot more, kind of pleasing, and billions of people look at this graph and they even bet on it or whatsoever, right? On the other hand, if you look at the fundamental concept of these tournaments, they are truly just the reduction trees, right? So let's do a very, very quick analysis about the fundamental property of these reduction trees. For n input values, the reduction tree will perform, half n operations in that first step. Remember, because we need to have one operation for each pair of the original values. So the first step will involve half n operations. And then the second step will involve only quarter n operations. And the third step will involve only 1/8 n operation. So if we add up this series, we will get n, we can take n out, and then we will have half plus 1/4 plus 1/8, and all the way to 1/n. And so this gives us 1 minus 1 over n. This is just a geometric series. So, it's a very basic geometric series. And then, we can take n inside, so that gives us, n minus 1. So this gives us the total number of operations that we're going to need to perform in order to do the parallel algorithm. So this is an important result. The result tells us that the parallel algorithm will need to do the same number of operations, order n, as the original sequential algorithm. In fact, it takes one fewer. It takes one fewer, right? So this tells us that we did not increase the algorithmic complexity of the computation. We're not blowing up the number of operations we need to do in order to do to get that result. But we can do many of these operations in parallel. So this is a very, very good, what we call the work-efficient parallel algorithm. We're not doing more operations, but we're doing them in fewer steps as long as we have enough threads. So in log n steps, if we have 1 million input values, it would only take 20 steps, as we already mentioned. And the average parallelism is actually the catch. The average parallelism is going to be much, much smaller than the number of operations you need to do in that first step. The first step involves 500,000 operations for a 1 million element list, right? But if you look at the average number of parallel operations across all the steps, the average is only 50,000. So what that means is that we're really over-provisioning the first step. We need to have 500,000 threads, all operating at the same time in order to process the million elements into 500,000 elements ready for the second step. So, the peak resource requirement versus the average resource requirement is so big that oftentimes people optimize it so that we don't have to over-provision all these, operations. If you go back to the tournament, this is easy to visualize. Let's say if you have 1,000 teams, 1,000 teams into a tournament. And, theoretically, we can just do 10 steps and get the champion. What's the catch about it? The catch is that 1,000 teams, if you want to really do 10 steps, you're going to need to provide 500 fields, right? In order for all those teams to simultaneously, determine the win and lose, right? And how many cities will have 500 soccer fields? So that's why people seldom have 1,000-team tournaments, okay? It's really limited by the number of fields you need to be able to, to whittle down the number of teams quickly in a small number of steps. So that's why, in reality, a lot of these tournaments can only handle, let's say, 20, 32 teams at most, usually 16 teams, because most cities will have up to maybe 8 soccer fields and so on. Okay, but for computing, theoretically, we can provide a very large number of threads. Why? GPUs, right? The GPUs can provide so many threads that we do have the option to be able to drastically employ a huge number of threads, and then we kind of just reduce the number of threads involved as we go, but going for good performance. Yes?
Oh, there's a typo. It should be 1 over a times n.
Oh, here.
Yeah.
Okay, because it should be 1 in the end.
So
Okay. In fact, this is like cockroach. So, in fact, I think I fixed it last time on this, but I forgot to fix the master. Oh, okay. So we'll do it later. But thank you. Okay. So let's go into a sum reduction example. So let's say we want to have a parallel implementation in GPU, in CUDA, and so we're going to recursively halve the number of threads. 2 values per thread in each step. So we start with a large number, and then in every step we're going to halve the number of active threads until the last thread generates the final sum, right? And so we assume that there's an in-place reduction using shared memory. That is, we load the original values into the shared memory, and then in every step, all the threads will be generating these partial results, but they don't write back into the global memory. They write into the shared memory, okay? And so the shared memory is held to hold a partial sum vector, and we're going to have fewer and fewer and fewer relevant partial sum elements until we have the final one. And this is also the first time that we are changing our memory usage pattern. If you look at the matrix multiplication, vector addition, and convolution, all those threads were accumulating their final answer in their registers, right? In their registers. And in the end, you write the register value out to the global memory. Here, we're writing these results into the shared memory. The reason is the threads now need to use each other's results in that computation tree, okay? So that's why you have to write that value into the shared memory so that your other threads can use your computation result. And it should become very clear when we begin to see the pictures like this. So we're going to do a thread to data mapping, and this is the first version, okay? The first version of thread index to data index mapping. And we're going to have thread 0, thread 1, thread 2, and so on to map to the data positions. We're going to map each thread only to the even data locations because they're going to be processing pairs, okay, pairs of elements. So if we need to process, let's say, 1,000 elements, we only need to have 512 threads. And we just map each thread to the even number of locations, and so even index locations. So thread 0 will be 0, thread 1 will be 2, thread 2 will be 4, and so on. After the first step, we will be producing 500 of these temporary results. We override the even locations in the shared memory. So the even locations now contain the partial sum, the pairwise partial sum after the first step. Now, if we look at the second step, now we only need to have 1/4 of the threads to proceed, right? We only need to have half of the original number of elements, and we only need to have 1/4 of the original number of data elements of threads to be able to sum them up. So we're going to only have thread 0, thread 2, and thread 4 active. But then, this is the important part. Look at this. Thread 0 now needs to add its result with thread 1's output. right? Thread 1's output. This is the reason why thread 1 had to write that into the shared memory so that thread 0 can use its output. Make sense? And shared memory is the fast memory where threads can see each other's results, right? Registers are totally private to each thread, okay? So then, in the end, for, let's say if we have, up to 8 elements, in the third step, thread 0 is going to add up the partial sum, of 0 through 7, and then, so then we'll have the result. If we have 16, then we will need to have one more step, thread 0 and thread 4, and then thread 0 will eventually add the final 2 partial sums to create the value. So in this particular mapping, we're going to have the sum of the original list in location 0, okay, in the location 0 of the partial sum in the shared memory, and thread 0 is going to be active all the time, and thread 1 will be only active in step 1, and it will become inactive. Thread 2 will be active for 2 steps, and then it will become inactive, right? So this is going to be important when we analyze the efficiency of the execution. So we're talking about a very simple thread, intuitive thread index to data mapping. Each thread is responsible for an even index location in the partial sum array, right? We map them into the even locations of the partial sum array. And then after each step, half of the threads will no longer be needed, so they will be dismissed. And then each step, one of the input comes from a increasing distance away. That is, when we look at the sum example, when we calculate each partial sum in step 2, the results will be coming from one element, 2 elements away rather than one element array as compared to that step 1. And then in step 3, one of the values will come from 4 elements away, right? So that's why the sum will be done in terms of the home index and then one element that is increasingly distant away from the position. So this gives us a piece of code that we're going to use as the base implementation. Okay, so this is the very first base implementation of a reduction tree. So we're going to define stride. Stride is the distance between the 2 elements being added, right? So stride will start with 1, so the element will be coming from the value will be coming from one element array. And in the second step, it should be 2 because it will be coming from 2 elements away. And then it will become 4 because the value will come from 4 elements away. So you expect that stride value to be double every step, in the execution. So here we start with stride 1. Okay, in the first step, all the data will be coming from one element away, right? And then we're going to test whether the stride has hit block dim, because we're going to have, let's say if we want to process 1,024 elements, we're going to generate 512 threads. So the very last addition will be adding element 0 with element 512, 11. Okay. So that's why it's going to be, the very last stride is going to be the block dim, away. And then every time you iterate, each iteration gives you one step, okay, one step in the process. So all the threads are going to try to do this. If the thread index multiplied, modulo stride is 0, that is, if t is a multiple of the thread, then that thread is supposed to be active. Okay, and so then we would add the partial sum of what the stride is responsible for. This is remember, 2 times the thread index is the home location for that in the data mapping, and we're going to add a value that is stride distance away into that value, okay? And then we accumulate that into the home location of the thread. So because the stride is going to increase from 1 to 2 to 4 to 8, so we're going to have fewer and fewer threads whose thread index is a multiple of that. When the stride is 1, everything is a multiple of 1. But when you have stride equal to 8, only 1 every 8 threads will be active, right? So here is a very important part that many people would miss, which is a sync thread. Between every step, I see a question.
Oh, I was just wondering, you said if there are 1,024 threads, the last operation would be adding 512 to 0.
Yeah.
So why does stride have to be less than block than
yeah. No. So basically, the last stride is going to be 512 away, right? So that's why this is less than or equal to the block dim. After you finish with stride equal to 512, then you're done, right? So it's basically just saying that because block dim is half the data size, right? So exactly, the data size is twice the block dimension.
Oh, it's twice the block.
Right. So that's why you're thinking about half. It's the half of the data size.
Oh, okay.
Perfect question. Now, so why do we need a sync thread? Okay, why do I need to have that sync thread before each iteration, right? At the beginning of each iteration. The reason is, we remember at every step, the threads are generating these temporary results. So in the next step, these threads are going to need its own result from the previous iteration and a value that is stride distance away, right? That will be generated by another thread. So before you can proceed to the next iteration, you want to make sure that all the threads have finished the previous iteration, so that when you tap into that distant element, the element is ready, okay? And the simple way to make sure that element is ready is to do a barrier synchronization, sync threads, and so that all the threads will finish the previous iteration before any one of them will start the next iteration, okay? So you can actually potentially do better than this. You can potentially have each thread to explicitly synchronize with the thread that will actually be providing that data. In fact, there are research tools that help you to do that kind of synchronization. But for GPUs, that's what we call the data sliding algorithms. But for the basic implementation, we usually just do a barrier synchronization and make sure that all the threads have completed step 1, so that when any of the threads start step 2, all these values will be ready, will be there. Then you can just do the addition properly, right? This is a conservative approach. This means that we're not going to generate any of the step 2 results until everything in the step 1 have been completed and available to other threads, right? Okay, so that's the sync thread. Now, what we just talked about made the assumption. That is, we need to, we're talking about a thread block that would, process twice the number of our block size of data elements. But we may have a lot more. We may have 1 million elements, right? So, block sizes are limited. The block sizes are only up to 1,024. So we need to be able to process a large number of elements. So this is usually done by, with what we call the segmented reduction algorithm. This is a terminology that means that we're going to be dividing and conquering the whole problem by dividing up the original list into the segments. So every thread block is only going to process one of the segments. And segment size is going to be up to twice the maximum block size that we can have. So let's say if we have 1 million of these data elements we want to sum up. So we divide them into 2048 because the biggest block size is 1024. So every thread block will handle 2048 elements. So each segment will have 2048 elements. So the thread block will load those elements into the shared memory, and then you do the reduction tree. So this is the reduction tree that you will take the block 0 part in the shared memory down into one element, right? So these element 0 in each of these segments give you the partial sum for the 2024 processed by that thread block. And then there are multiple choices. The simple one is you can write it into a partial sum grid array so that there should be very few of them, and then you can use the CPU to just sum up all these partial sums from each thread block. Or we can also, we can also use atomic operations to accumulate those partial sums into a single answer, and that will become clear when we talk about the histogram pattern. So we'll cover that alternative soon. And if there are only a small number of partial sums, the host can simply take, just copy that partial sum array back, and then just sequentially add them up. So that would also complete the work. So in MP 5.1, we're going to use this approach. We're going to have you to take original list, and then each thread block is going to take a segment, and you generate a partial sum output array, and you copy that back to the CPU, and the CPU will add up the partial sum array into the final sum. Okay? Because the point of 5.1 is for you to exercise the reduction tree implementation inside each thread block. Okay? So there are a few observations about that approach. If we analyze what's going on, in every iteration, we'll have two control flow paths for within each warp. Okay? And threads that perform addition and threads that do not perform addition. And so the threads that do not perform addition still consume execution resources. So let's go back to here, to this example. We have thread 0, thread 1, thread 2, thread 3. These threads are all in the same warp. Right? They're in the same warp. So after the first step, 2 of the threads will no longer be active. So they will fail that if test, right? Remember that if test that we have here? If T is T modulo strike, T is a multiple of strike. So when T is 2, only the even ones will succeed with this test. So this if statement is going to create a control divergence. Okay? In the second step, all the odd ones will fail, all the even ones will succeed. So you have 2 paths, right? And then the next step, all the multiples of 4 will succeed, and the rest will fail, right? So within the same warp, you're going to have control divergence in every step of the way, except for that first step, right? After the first step, you're going to have control divergence in every warp, So it's a kind of a base implementation, but we're going to have a lot of control divergence in this. This is very different from the boundary check of matrix multiplication or vector addition. The boundary check divergence only happens at the very edge or very end of these data structures. But here it's going to be a systemic problem. It's going to be present in every warp. Every warp after the first step, you're going to have control divergence. Okay? Yes?
So what if, for example, after
That's a great idea. I like that. So, we're going to go in that direction for sure. Very good. Okay. Keep, I want you guys to, to keep thinking, with us, right? Absolutely. So, the bottom line is when we look at that kernel, the kernel looks fine. It has the parallelism. It uses shared memory, but it has no more than half of the threads executing after that first step. And so all the odd index threads are disabled after the first step and so on. So after the fifth step, okay, so this will continue for 5 steps. After the fifth step, the stride value is going to be greater than 32, right? So then this can go on, after that first step, fifth step, entire warps will become inactive, right? So that's good. Then you don't have control divergence in those warps anymore, right? But whatever remaining warps that we have will still have control divergence. And the control divergence is such that only one thread will be active, and the other 31 threads will be inactive. So every time you take the warp into execution, you only have one thread making progress, and all the other 31 threads will be still using execution resources, but they don't produce anything. So this is a very, very inefficient way of using your execution resources, right? So some would still succeed, but divergence would, it will be extreme divergence in those threads, warps. So this is why the thread index usage really matters. When we map this into in an intuitive way, we can actually create these very, very inefficient use of threads and also lots and lots of control divergence, along the way. So we can actually, shift the index usage to improve the divergence behavior, but we need to be able to play with the different ordering of summation. This goes back to the commutative and associative properties. We're going to actually add up pairs in different orders, but you will get much better efficiency out of this. So the strategy is exactly what we're talking about just a minute ago here. We always pack the partial sums into the first locations in the partial sum array. We don't let them spread out the way that first algorithm is. We always make sure that all the partial sums are packed into the first portion of your shared memory array. And then we keep the active threads also consecutive all the time, okay? So this is what we do. We don't need to move anything simply because we can choose what the pairs, to choose the element that will be accumulated into each of these home locations. So let's say we still have, use the small example of 16 threads, and we're adding up 32 elements, right? We're adding up 32 elements. So we're mapping all the threads into consecutive data locations now, not every other one, okay? We're mapping them into consecutive locations. So when we add up, do the first step, when we perform that first step, we're going to add the home location value, not with its neighbor, not with its neighbor anymore. We take the element that is block size away, okay, block size away, and add that into the home element. So this is 0th position and 16th position, and this is position 1 and position 17, and 2, 18, right? Every element is going to be, pair is going to be 16 locations away from each other. But after we add those pairs, we put the result into the home location, and look at that, the home locations are all consecutive with each other, right? So now, when we do the second step, we will use half of the threads. We still use half of the threads, but the half of the threads will be consecutive, okay? So we're going to use half of the threads, and they are consecutive with each other, but we're going to add the partial sums of their home location and now quarter of the original data size, right, away. So the stride now starts with the biggest value, right? The half of the data size, and then we divide it by half. We have it every step of the way. So the stride value start with the maximal value, and we just have it in each step. And we keep writing into these consecutive locations in the shared memory until we end up with only 2 of them. The last step will create the final sum, right, for the thread block. Make sense? So in order to convert from the previous version to this version, we actually don't need to change a lot of code, okay? The piece of code that will do this, will implement this particular assignment strategy is going to look awfully similar to that first version. Remember, we want to start with the maximal stride value. So we initialize it to stride value to block dim.x, right? So we ended with that in the previous version, but here we initialize the stride to the maximal value. And we keep testing whether the stride reaches 1, because that's the last iteration, okay? And in each step of the way, we divide stride value by 2, right? We have that stride value every step of the way. We still need to do sync threads, because every step, we still need to rely on another thread's result, right? So we still do sync thread to make sure that everyone finishes. And then here, when we test whether the thread should participate, we take the thread index. We no longer do that modular thing. We see if the thread index is less than stride, because we're using the first so many threads in the warp, right, to be able in the thread block to do that addition. So in the first one, as long as you're less than less than or equal to the block dim, which means that every thread will be active. The next one, as long as you're less than or equal to the number of half of the block dim, then you should be active, right? So in every step of the way, we're now testing whether your thread index is less than the stride value of the moment, okay? And that stride value is going to be reduced by half each step. So that's why each step will involve half and half and half of active threads. Make sense? So this piece of code, if someone has not gone through this exercise, has not gone through the thinking process, this piece of code and the other piece of code look the same, okay? And most people will not be able to tell the difference between those 2 pieces of code. But the performance difference can be tremendous, okay? And I would really encourage you to try both versions, okay? Just see, how the performance differ. So if we do a quick analysis of this piece of code, for a 1024 thread block, we can handle, load 2048 elements into the shared memory, okay? And then, so as we go, there will be no divergence whatsoever in the first 5 steps, because we're going to just have fewer and fewer warps. Entire warps will be turned off, right? So after the first step, half of the threads will be turned off, which means that 512 threads in the upper thread index space will be turned off. And they are entire warps. So the entire warps will be turned off. So the half the warps that are active, they are all active. All the threads are active. So we don't have any control divergence. So we'll have, essentially 1024, 512, 256, all the way down to 32 threads, consecutive threads active. After the first 5 steps, starting with the 6 steps, we will begin to have control divergence, because now we have fewer threads than the warps, right? The number of threads in a warp active. So that's inevitable. When we have fewer threads than the warp size active, we will have control divergence. But so the final 5 steps will still have divergence, but the number of active threads in the warp, in that final warp, is still going to be 16, 8, 4, 2, and 1, compared to the previous case where all the threads that are still limping along will only have one thread active, right? So this, even with this control divergence, you will still be making progress faster than the other algorithm. So not all the control divergence are the same, because this algorithm, even though there's control divergence, you're still having more active threads each time a warp comes in, and that will still make faster progress than the alternative. Okay? Does that make sense? Okay. This is something that you really should go back and explain to your roommate again. Okay? So this is yet another dinner conversation you should have with your roommate, and make sure that you can smoothly explain all this during dinner conversation, and drawing a picture on a napkin if necessary. Okay? So one thing that is, did I see a question? Oh. So one thing that I also want to make sure is you understand the concept of parallel algorithm overhead. This is something that we always talk about in an abstract way, but this is an opportunity for me to point it out to you in a very concrete way so that you can always have that intuition. When we parallelize these algorithms, from sequential to parallel, we oftentimes add overhead. Okay, so even though we are doing n operations in the parallel algorithm, and also n operations in the sequential algorithm, but each operation in the n, each of the n operations may be more expensive in the parallel algorithm than the sequential algorithm. So this is a good example. Remember, in the sequential algorithm, we really don't need to do anything to start. We just put the pointer to the first element, and then we just start traversing the list, right? But here, in order to be able to do that parallel computation in the thread block, we first need to calculate the starting position. We're doing the segmented, so this is where we do the segmented reduction. Each thread block is going to go to the initial location, the start location of of that thread block. And here, because every thread block is going to take care of 2 times block dim, right, elements. So your block index times that number is going to give you the beginning location in the input array, right? This should be very familiar to you now, after the vector addition and so on. And then each thread is going to be loading from the start position plus the thread index, right? Plus the thread index for that first half of the element. And then every thread is going to go increase to the block dim plus thread, and everyone will be loading the second half of the input segment, right? So this is actually one of the questions in the exam, right? In the vector addition question, and we're preparing you for these kind of loading patterns, right? So you don't have to just process 1 input element per thread. You can be processing 2 input elements per thread, 4 input elements per thread, and so on. Now, if we go down to the iterations, remember in the sequential algorithm, we just increment the pointer and then access the next input element. But here, we need to double the stride value. We need to shift the stride value to actually half the stride value by shifting the value to the left by 1, to the right by 1. And then we need to do sync threads. We also need to do the stride is less than, do it if then else. And we also need to do the index, adding, thread index by the stride value, and then access 2 elements and add them together. So this is a lot more work than just going to the next sequential location, access the value, increment the pointer, access the value, right? So this tells you that every step of the reduction tree parallel algorithm is a lot more activity, okay, than the sequential algorithm step. Steps are not always the same. So this means that the parallel, when you have a parallel algorithm, you're going to have, the number of operations compared to that sequential algorithm, even though the number of operations both n in serial and parallel, each operation can involve a lot more complex address calculation, and intermediate result manipulation. When you work on your project, at some point this will begin to show up. You can actually use certain simplifications on your index calculation, and you will actually begin to show up in terms of faster execution speed. So this tells us that even in parallel execution, the overhead that we spend in each operation, accessing memory, the index calculation, can actually still be significant in terms of the final performance. So if another way to look at it is that if you take the parallel code, okay, if you just take the parallel code, that kernel code, right, and instead of launching a whole lot of threads, with a kernel code, we can serialize it. We can actually use a loop. Okay, we can use a loop and take the kernel code and then just iterate through all the segments. Okay, and within each segment, we can use the loop to iterate through all the all the elements in every step. We don't have to launch parallel threads. But if we do that, the sequentialized version of the parallel code will run significantly slower than the original sequential code where you just use a pointer to traverse all the elements. So this is a classical example of the parallel code will run slower if you use very, very few parallel processors. Okay? And so oftentimes, when we have a parallel algorithm and we want to beat a efficient sequential algorithm, oftentimes we need to have at least 8 processing elements or more in order to be able to beat an efficient sequential algorithm. So this brings us back to one of the conversations I had with the Intel executives about more than 10 years ago now, probably 12 years ago. I used to direct a research center funded by Intel and Microsoft called Universal Parallelism Research Center. So every year we have these meetings with Intel and Microsoft executives, and we discuss the sort of the parallel multi-core roadmaps and parallel algorithms and then parallel software. So there was a conversation about multi-core architectures. So basically the executives said that we're going to provide the field with a roadmap where we start with sequential processor, and the next generation will give them 2 cores, right? And the next generation will give them 4 cores and 8 cores and so on. That sounds good, and I said, wait a minute, it's not going to work. And all these executives look at me and say, what do you mean? What's wrong with this 1, 2, 4, 8? Everyone can think it will work. I said, no, it's not going to work. I said, the reason why it's not going to work is precisely because of this phenomenon. When you have a parallel piece of code and you run it on a small number of cores, because of the parallel overhead, that 2-core execution will likely be slower than the original sequential algorithm running on a single core. Why would people bother to write parallel code in that case? They will not bother to run parallel code until you have at least 8 cores in your system. Okay? These executives were very mad at me. They were really, really mad at me. And when you have someone, you're funding someone. Oh, I'm being recorded. So when you give someone money, they should just tell you that everything is great, right? So what do you ask us to do? I said, well, at least put together a 8-core system that may or may not work perfectly for all the software. In fact, for the sequential software, this 8-core system may be slower. But when people write parallel code, the 8-core system should be able to beat the best single core that you have running on the best single sequential algorithm. And they said, go away. Okay. So I did go away, by the way. So after the third year, I resigned from the center director position. I just say, I can't deal with this. So I resigned. And then, sure enough, the year, I was talking to another company on the side, and another company says, how do we get parallels to work? I said, can you produce an initial version of 8-core systems? And this other company, started with N, told me that, yes, we can do that. And that's called G80, the first CUDA GPU. And they said, we're going to produce this chip that will probably run terribly on sequential algorithms, and it will be much, much slower than the CPU cores when you run sequential algorithms. But if you can write very parallel code, this chip is going to really, really fly. And I spent a whole week in Santa Clara and looking at the chip and then looking at the code and so on. I said, okay, this works. So I don't know the rest of this is history, because I ended up working with the chief scientist at NVIDIA, David Kirk, to write the textbook that you're using right now. And the key of that whole GPU movement is that they provided 8 cores right from the start. Okay? And the parallel code can actually beat all the sequential code running on a single core. Okay? And that was the important part of that history. Otherwise, this whole GPU revolution would have failed. So this is what I call the discontinuity in the field. So this is something that I want to make sure that all of you, as essentially as engineers, and eventually I want some of you to become executives that can actually make product lines to work. Okay. And so when you make billions of dollars, you can come back and donate to the next ECE building. Okay. So essentially, when you are beginning to think about a change in product, roadmap, one of the most, I would say, most, tendency for the executive is to say, here's my current products. Do I have an incremental way to make my product into what needs to be, right? So if I have a sequential product line, I need to have a parallel product line. Let me start with 2 and then 4 and 8. So it's a very smooth transition. Turns out that in most of the innovations, when you change your paradigm, there's no real path to do that sequential transition, simply because of these kind of things. When you change your paradigm, your overhead and a lot of these things are going to require you to do a fairly big jump. So that's why this is a very good example of what we call the innovator's dilemma. And the current winners, the current dominating players in industry, oftentimes will have a product that is very, very good, okay, that has been very good, very successful, but they know that they need to evolve the product or even revolve the product into a very different paradigm. But there's no good path to incrementally evolve the product line. So that will take a startup company to essentially break all these desires of smooth transition, because that's what it takes. Sometimes that's what it takes. And you know what? We talk about innovation dilemma all the time, and we talk about these things, but this is an opportunity for me to relate that to one of the very concrete things that you see in your code. And this is probably the smallest example I can have to tell, to explain what innovative dilemma really is. And they show up in so many of these, different areas in the industry. But this is probably the simplest example I can have in terms of innovator's dilemma. Okay, so I have a few more minutes, and I want to make sure that I tell you a kind of a little story. The little story is about an old engineer, and so there was a factory where you have these big machines, and so there was a old engineer who has been maintaining those big machines over the years. And when it comes time for the old engineer to retire, the owner says, I need you to train your replacement so that I can keep operating this factory. So the engineer trained a younger person, and with all the, all the procedures and so on. Okay, all the procedures, and then the old engineer retired. At the day of the retirement, the owner says, I'm still a little bit uneasy about this. Okay, if everything fails, if the young engineer cannot, get everything to work, can I call you? And the engineer said, okay, here's my phone number. You can call me if everything fails. Sure enough, in 3 months, the machine stopped working. Okay, and the young engineer, used the procedure left by the old engineer, every procedure, and nothing worked. Okay, so the engineer said, okay, I have not, I don't have a case for this situation. So let's call the old engineer. And the owner agreed. So the owner called the engineer and said, can you come back? And the engineer said, would you pay me for my time? And the owner said, yes, I'll pay you for your time. And said, how much? $15 an hour. Okay, so fine. So the owner said, $15 an hour, come back and fix it. The engineer came back and looked around and, turn a few knobs and then, thought about it a little bit, and went to the back of one of the cabinets and gave it a real big kick. Okay, and the whole thing started. Okay, so everything worked after that. It took 15 minutes for this to happen. So the owner says, great, 15 minutes, $15 an hour. I would pay $1/4 of $15, but I'll be generous. I'll pay him $15. Okay. So the bill came. The bill was 1,000 times 15, so which is actually $15,000. And the owner was very angry and said, how can you charge me 1,000 hours for what you did in 15 minutes? The engineer explained, 15 minutes for going in and kick the machine, and 999.75 hours for all the hard work and study that I had to do over the years that you failed to pay me, and I'm going to charge you for all that time to get to the point where I can figure out where to kick. Okay, so if you look at the code that I just showed you, the code is actually very, very small. Okay, there are only a few things that you need to do in the code, and when you move from a very, very bad piece of code for that control divergence to a good piece of code, there are only a small number of changes, right? It may not even be obvious, but it takes a whole lecture for you to really understand the difference between the two pieces. And that's the nature of parallel programming, and that's the nature of a lot of these highly, highly, optimized systems. Until you really understand all the ins and outs of these things, you will not be able to tell the difference between a piece of code that runs 100 times faster than another piece of code. Okay, so next, Thursday, Carl is going to be here to finish up the CNN and the kernels. Okay?
Should I also do an ND problem?
Yes, exactly. Yeah, perfect. Yes.
I have emailed the Andrew to.
Yes.
Yeah.
Okay.
So would you just
Okay.
make sure?
I'll make sure that he responds. And also there's another one. Yeah.
Yeah.
Okay. Yes.
Here's the little table for the page.
Hold on. I want to catch those. Okay, page 19. Okay, right here. Okay.
For the calculation part, the 1024 divided by 32.
Oh, it should be 32. Oh, not 16. And then it's 2 to the 5th. Okay, thank you. Excellent.
Quick question. So,
Yeah.
what if my device has I'm doing my own stuff, what if my device has a 2 GPUs inside, would it when I use CUDA as a device,
Yeah.
I create all the memory
Yeah,
blocks.
yeah.
Later on when I do the computation, how do I make sure those two actually align together? Because do I need
Oh. Okay, so you're using 2 GPUs?
Yeah, but there are two different kinds. One is a 90 Ti, and another one is 20.
You need to do what we call the device synchronize. So look at device synchronize.
But that's the only thing you need to do, or like do you have to like line up with the slowest one?
Line up with.
With the slowest one, because when I do the rendering, like I push the
Oh yeah.
I push the most to the 10x speed, but like
Yeah.
90 Ti is like still like I'm doing partial rendering. So at the end I have to like integrate them together. So I'm not sure like
Okay.
do I need to
I have not done that myself, but if you go onto the forum and start with the device synchronize, you should be able to find people talking about this. Okay, and start with that, and tell me what you find. Okay. Yes.
So in regards to the exam,
Yeah.
I'm not sure how well I did, to be honest.
Yeah. We will have all the exams graded tonight. So yeah, we're almost done. So we'll let you guys know.
Right. So yeah, but my concern is should I be concerned if I didn't do as well on this exam as I wanted to?
Yeah. Come and talk to me. Basically, the exam accounts for, I think, 20%.
Right.
Okay. So depends on your score. So come and talk to me next Tuesday. Okay. Yeah, I'll help you to analyze it. Okay. Yeah. Okay. Yeah.
Is your office in CSL 215?
Yeah. This afternoon. Okay. Come close to 1:30 because I have a faculty candidate interview. So come early. Okay.